Um, so here we are, we're at U sub. I remember writing this sentence. When we are integrating, we are simply, asterisk, reversing the process of differentiation. I believe at the bottom of the page it says there's nothing simple about this. So let's take a look at an example of differentiating and then think about reversing the process. So we have the chain rule, and that's not that U substitution is exclusively reversing the chain rule. It's actually a really strong tool that does a lot of things. But the one we're going to focus on for the most part, we're going to see a couple different, but we're going to really think about U substitution as mostly reversing the chain rule. When we do the chain rule, when we take a derivative, when we go in one direction, we take a composite function and we end up with a product of two functions, right? So we take the derivative of the f of g of x, we have to start out with g prime, and that g prime is multiplied by the f prime of g of x. So when we do something like sine cubed of x, which of course is bad notation, but what we actually use to begin with, we've got to take the derivative of the sine of x, but the sine of x is being cubed, which means that we end up with first, because of the chain rule, what are we going to start out with? What am I going to write in blue? Cosine, yeah. I'm going to start out with cosine of x. Yeah, that's fine. That's why I kind of like went a little bit deeper and put, what are we going to put in blue? And now we can do the actual power rule and write the 3 sine squared of x. So the sine of x but squared, which can be written then more compactly as 3 cosine x sine squared of x, and just as good and equally as 3 sine squared x cosine x. So those 3 lines are all equivalent. And if I had to integrate any of those 3 things, the one on the bottom matching my integral, I am just reversing the process. That integral on the right is just sine of x cubed plus c. So because derivatives and integrals, are opposite, are inverse operations, they oppose each other. If I happen to know that I can get this by taking the derivative of sine cubed x, then I know that the integral of that is sine cubed x plus c. But you don't always just know that. It's not like this is just going to be obvious to you. So that's what U sub is for. That's what this next sentence says. Anytime I told you to use the linear chain rule, especially in integrals, if that doesn't work for you, you can use U sub. So in example 2, our first problem, many of you can already do this problem without going through the U sub process, but I'm going to show it to you with the U sub process, so that A, you understand, how to do the U sub process, and B, it's a backup if you're finding yourself not able to, deal with the linear chain rule inside of an integral. So whenever you have a linear argument, U sub is going to be an option. What we're going to do is we're going to take that linear argument and we're going to define it as U. U equals 3x minus 4. Okay. So, and in any case that we're doing the U sub, we're taking part of our integral and labeling it as U equals. Sometimes it's a guess and check. Sometimes you have to mess around with a couple things before you actually find the right thing to make U. And if you don't do the right thing, you won't be able to get an integral that works. Because in the end, you're turning this integral, our goal is going to be to turn it into a must-know. We're going to end up in a must-know situation when all is said and done. The next thing we have to do is we need to take the derivative of that U. Now, in the language of derivatives, we would write du, don't write this, du over dx. That would be in the language of derivatives. But in the language of integrals, we don't do the with respect to dx, we just use the chain rule on the other side. So we say du equals, take the derivative. The derivative of 3x is 3. but since we took the derivative of x, we're going to write dx. Okay. So instead of du divide, which again, this notation doesn't mean divided by, but understand why we're okay with doing this. Instead of du divided by dx, we just have du, and then we have that dx multiplied on the other side. There's a lot behind the scenes that doesn't make what I just said correct, but it's enough to get you to understand why we write it that way. So that's what we've got there. What we need to do next is we need to make an integral in terms of u instead of x that is algebraically equivalent to the integral that we have. That really is the key. If you're not algebraically equivalent, you're writing the wrong thing. So our integral has 3x minus 4 in it, and it's got a dx. So I have a dx here, but I know what 3 dx is, but I need to fill in for just dx. So I'm going to divide both sides of the orange equation by 3 to find out that dx equals 1/3 du. So now, an algebraically equivalent integral. I have the integral. Instead of 3x minus 4, I've said that 3x minus 4 is u. So I'm going to write u to the 5th power. My u's in blue, my 5's in black, because the 5 came from the function. That is the function we're integrating. We're integrating something to the 5th power. So that 5 actually is the function. And we know that dx is 1/3 du. So this is all multiplication. I'm going to bring the 1/3 out because it's a coefficient, and I'm going to write the du there. The integral that I have is two things. It's a must know with a coefficient in front of it, and it is algebraically equivalent to the integral that we have to solve, because I've replaced 3x minus 4 with u, and I've replaced dx with 1/3 du. Right. So now we integrate. I still have my 1/3. I do the power rule on u to the 5th. That gives me u to the 6th over 6. And since I've integrated, the du is gone. And I'll write a plus c so that I'm accurate. So we end up with u to the 6th over 18. Yep. Questions on that? For those people who have the linear chain rule down, you could have done that without all of that, right? Raise the power to 6, divide by 6, also divide by 3 because of the linear chain rule. So that's where the 18 comes from. Yeah. I do want to do this, although it is really simple. Some of our other examples won't be so simple, and they'll mix some numerators and denominators. We integrated u to the 5th du, and that u to the 5th du, according to my my work up at the top, is 3x minus 4 to the 5th. Oh, sorry, we did, my bad. I forgot the 1/3. This is what I want. Sorry, we changed it to 1/3 u to the 5th du. So that is 1/3 times 3x minus 4 to the 5th times du equals 3 dx. And those 3's cancel. And that gives me exactly what I wanted to integrate. So this is what I mean when I say algebraically equivalent. So that's all that is down there. Just me showing you in pictures that we did something algebraically equivalent. We did 1/3 u to the 5th du instead of 3x minus 4 to the 5th dx. And we did the same thing. Questions on that? All righty. Number 2 has a 6 in it. Your goal in one of these problems is to look for something that when you take its derivative, you find it. And the one thing that might be off is the coefficient. So if you find something that you have, and the only difference between what you found and what you have is the coefficient, you're good. That's really what this step is for right here. Oop, I didn't drop. That's what this step is for, just fixing the coefficient. So we have 6x squared. We have x cubed plus 4 being raised to the 5th power. Is there something there that when I take its derivative, I get the other something? What is that? What is the thing that I take the derivative of? Plus 4. Plus 4, yeah. So we're going to do x cubed plus 4. Yep. They would be. Well, we want to try to get as much as possible in because we want to simplify this integral as much as possible. So we will make u x cubed plus 4. We will take its derivative and we'll get du equals 3x squared dx. But we don't have 3x squared dx. We have 6x squared. So we want to take this line and make the right-hand side say 6x squared dx. So we're going to multiply by 2. Yep. A lot of times, this whole process is just to get the coefficient right. So that tells us that 2 du equals 6x squared dx. And that's exactly what I have. Again, everything inside of this integral is pure multiplication. So breaking that 6x squared dx is not a problem because it's just multiplication. So what we end up having really is the integral of, I'll start with the blue. We have u to the 5th power again. We actually end up with the same must-know integral. I probably did that on purpose. That's being blue. I need to make my blue a little bit lighter so it shows up on the screen a little bit different than my black. U to the 5th times 2 du. So I'll put the 2 on the outside as a coefficient, and I'll put the du where it belongs. So we end up in almost exactly the same place we were last time, short of the coefficient. So we'll end up with this time 2 times u to the 6th over 6. Just trying to think of what colors I want to use here. What did I do? 2 u to the 6th over 6 plus c, which is u to the 6th over 3 plus c. And again, what did we integrate? We integrated 2 u to the 5th du, and that is algebraically equivalent to, let's put these black. Yeah, I didn't change colors up here too much. A 2, x cubed plus 4 to the 5th power, 2 u to the 5th times du, which du, middle line, is 3x squared. We integrated something that is algebraically equivalent if I just bring things around to what we were first given. Thank you. Yep. 3x squared dx, absolutely. I'm not sure what you're asking. Yeah, no, this, geez. Yeah, no, you know what? I'm glad you asked that because I totally lost track of that. Yeah, no, we do want to do that. I would have realized that later and been really mad at myself. Yes, we do. Plus 4 to the 5th. Yeah. Yeah. So that, right. Our problem was in terms of u. So we have to go back and, right. Our final answer should look like this: 3x minus 4 to the 6th over 18 plus c. So yeah, the last part of these ones should always be going back in terms of x's. Now, when we get to definite integrals, ones with the limits, we actually won't have to do this step. We'll see that when we get there, though. That won't be today. All right. No, good catch. Thank you, Jack. I would have been really mad if I had to go back and do this on like 4 problems. So we got x cubed over 4, x cubed plus 4 to the 6th over 3 plus c. Yes, your final answer should be back in terms of x's. Yep. All righty. Number 3, a little bit more of a hunt. We need to find something inside of this problem that when we take its derivative, it's there, except maybe the coefficient just isn't right. If I take, well, no, because e to the x isn't there. Right. So yeah, you're generally not pulling a, usually your u is not a composite function because you would end up doing the chain rule inside of that next step and you would have way more things on the right than you actually have in your function. So square root of x. Watch what happens if I make u equal to the square root of x. What's du? 1 over 2 root x dx. And I think now is the point where my bottom line, where I just check and look for the algebraic equivalence, is going to happen. Du is 1 over 2 root x dx. So what I'm really looking for in that line, the 1 is a placeholder because I have nothing in my I have nothing of significance in my numerator. The whole function in du is that 2 square root of x, but it's in the denominator. And that is what I have in my number 3. I have that square root of x in my denominator, but I don't have the 2. So I need to make my right-hand side look like what I have in my integrand. Yep, so I've got 2 du equals 1 over square root x dx. Boom. So we will integrate. We will not, well, we'll do our substitution. So let me color this. We had, this is our u. It is just e to the u. Yeah, and it does turn out that we're in a situation here where I could write this as e to the u over u, but that is not correct because that square root of x dx is this stuff right here. And the 1's just a placeholder, so we don't need to find that. I mean, I could write a 1 in front of my e to the square root of x. But we'll see when we go down to that last thing where I talk about algebraically equivalent, we'll see how it all kind of comes through. So let's see, we have we have the integral. We have e to the u, which I want in blue. Yeah, and then for dx, so for 1 over the square root of x dx, which is all of the orange that I have highlighted, that is just 2 du. So that square root of x in the denominator and the dx outside becomes 2 du. It's the du. Du has that root x from the denominator inside of it. Before we actually iterate, let's go down to that bottom step where I check it. 2 e to the u du is equal to 2 e to the square root x, because u is the square root of x, times du, which is 1 over 2 square root x dx. My 2's cancel. My e to the square root of x slides up into the numerator. And 2 e to the u du is algebraically equivalent to e to the square root x over square root x dx. If it's not, you're not doing the right thing. So things disappear like that. Because there's cancellation that's either going on in your head or you explicitly write it out at the bottom to check it, like I'm showing you here. You've got to figure out how you're going to get these problems correct. So anyway, world's easiest antiderivative. An antiderivative for 2 e to the u is, exactly, so our answer is 2 e to the u plus c. And then that's just going to be 2 e to the square root of x plus c. And in the end, too, the other side of this is if you took the derivative of 2e to the square root of x plus c, you would end up where we started with, because you'd have to do the chain rule on square root of x, and that would put a 1 over 2 root x in your denominator, or I guess a 1 over 2 root x out in front of everything, and that's where that root x came from. It would then cancel with the 2. The 2's would then cancel, and the derivative of c is 0. Okay. Last but not least, I think this is a good one to see. They'll never just, this is actually not expected to know on the AP test. But to do tangent or cotangent, to do that integral, our must-knows aren't based on the functions, right? Like the must-knows are based on derivatives we already know, but you can actually use substitution to do either tangent or cotangent, because the integral of cotangent of 3x is the integral of cosine 3x over sine 3x dx. That's just trig identities, or definition of what cotangent is. All right. So we need to define a u, see if its derivative is in this function somewhere. And there's kind of two ways to do it, and one of them doesn't work. So who wants to guess what our u is? We only have two options. U would never be 1, because then du would be 0. 3x over 3x doesn't exist in that function, because 3x is an argument. I like these things that we're saying, though, because let's say them now so that if you think them later, you can remember. Yeah, there is no 3x over 3x in that function. It's also not in that function. There are only two things in that function, from my perspective. Yeah, cosine of 3x and sine of 3x. So which one are we going to make our u? All right, I love it. We just picked the wrong one. Yeah. Well, no, I want to see what happens when we go when we pick it and we go the wrong way. Remember, I said sometimes this is a guess and check, right? So when you're in a situation where you're doing a little bit of guess and check, you need to see what goes wrong as well as what goes right. So when we do u equals cosine 3x and we do du of negative sine 3x, which is still not correct because there should be a 3 in front of it. Yeah. The problem with this is when you go to do algebraically equivalent, negative 3 sine x dx, you would need a sine of 3x being multiplied by a dx, which we do not have. We have sine 3x in the denominator, so we have 1 over sine 3x being multiplied by a dx. Right, hey. You should, yeah, I do, but you could also just use follow me print color. Okay, yeah, I do, but not right now. Yeah, later, but we're doing u substitution, so this is more important. Talk to you later. Oh, she's down there now. Yeah. So here's the problem, and I think this is really important to know. Sine 3x dx is not in here at all, because sine would need to be in the numerator in order to be being multiplied by 3x. Or yeah, sorry, dx. I said 3x, but I meant to say dx. Close enough. So that is the key. There is no algebraically equivalent sine 3x dx here. When you got to the bottom and tried to do this, things wouldn't work out. I've definitely seen people do it this way and do wrong things, but the right way to do it, there's no way to do it because sine is in the denominator. You have 1 over sine 3x. So the thing to pick isn't cosine 3x. It's also not 1 over sine 3x. That would be a nightmare because you'd have more chain rule going on. Because you'd have sine 3x to the negative 1 power. It's just to pick sine x. Sine 3x. I keep saying x, but yeah, sine 3x is enough because what you're going to end up with is 1 over u. When we make sine 3x our u, we're going to end up with 1 over u. And the derivative of sine 3x is, yep. And in this case, we do have cosine 3x dx being multiplied in our integral because having a numerator times something is as good as having that something in the numerator, right? But we don't have 3 cosine 3x. We have cosine 3x. So the whole thing needs to be divided by 3, which we're going to do by multiplying by 1/3. Okay. So, you know, in the end, you want to go as simple. You want to go simple. Going 3x is actually too much. You could make this a 2-part u sub by starting with 3x, but that's why I'm so big on the linear chain rule. Like we know how to find the derivative of sine 3x because we understand the linear chain rule. So we actually didn't have to do this in 2 parts, making u 3x and then getting a new integral and then having to like make a v sine of u. Ugh. We don't want to do that if we don't have to. So that's why I'm a linear chain rule guy, because we can kind of just do all of that right in here. Okay, so in the end, algebraically equivalent to our integral is we have something over u because our u is the denominator, and that thing that we have over u, how about I do this, is du. So I can write it this way, but I still need that 1/3, right? Yeah. So yeah, and that is no different. This is a good time to talk about it. There's no difference between having 1 over u du, or a lot of times they'll just slide that du up into the numerator. So if the numerator is 1, a lot of times the du just shows up in the numerator instead of tagged on at the end. Desmos probably doesn't like that, but I'm not really sure. So we'll do that. Antiderivative for 1 over u is ln. Yep. Ln absolute value of u plus c. Didn't forget it, which makes the answer to this problem 1/3. My color coding is right out the window. 1/3 the ln of the absolute value of u, which is sine 3x plus c. Yep. And again, algebraically equivalent, we integrated du over 1/3 du over u, right? And that is equivalent to 1/3 du is 3 cosine 3x dx, and u is sine 3x. Everything's being multiplied. The 3's cancel, and that gives us cosine 3x over sine 3x. Slide the dx out just to make it look exactly like what we started with. Algebraically equivalent. We integrated something algebraically equivalent. Yep. Yeah. All right. No, you've got to be able to find it. I mean, that's the thing. You've got to be able to find that derivative there. Let's identify our u's and du's for 5 and 6, and then have you guys finish off the process. Oh, sure. Yeah. Sorry about that. Yep. Yeah. All right. So while I leave this up for a second, this next one's a good one because there's a lot of wrong and right guesses you can make here. What's that? Are we? Yeah, I guess so. Yeah. Yep. Yep. Actually, I think 5 is a little trickier than 6. All right. You good, Ethan? I think so. Yeah. Yeah, no problem. Always yell. I'm never physically aware of myself doing that. So, number 5, we've got to identify something and then find its derivative inside the something as well. One minus cosine x is not in there. Okay. What's the derivative of 1 minus cosine cubed? And so 2 questions. You can answer whichever one you want first. What's the derivative of 1 minus cosine cubed? And is that thing in your integral? Sine is there. Right. Right. This would have like a sine squared in it. Or sine, yeah, it would it would have a cosine squared in it because arguments never change. But yeah, the derivative of 1 minus cosine cubed would have cosine squared in it because you'd be doing the power rule, and there are no cosine squareds here. So that is not our u. That is not an eraser. Okay, so the next plot was u equals sine x. But here's the thing about this one. If u is sine x, du is cosine x dx, which means you have a single cosine directly being multiplied against a dx, which we don't, right? We have 1 minus cosine cubed x being multiplied against the dx. But that's going to give us the same problem. We're still going to have a cosine squared. It's never 1 because du is 0. It's not the whole thing. I don't have to rewrite it, but maybe this shows the one thing that we haven't said yet, which is the right answer. Just plain old cosine x. Because if I make u cosine x, does my du show up there? It does. Derivative of cosine x is negative sine dx. We just have a coefficient to fix. You got it. So u is cosine x. How many times have I said our notation for powering a cosine is like the worst? Because it doesn't make you feel like cosine is just there. So I'm going to identify the u here and let you try it. U equals cosine x. We'll see what you come up with. I think the next one is a little bit easier in number 6. Let's see if we have a u and we can find its du. So what's the u? It will work if you do. It's funny how it will work if it's ln x. But since that ln x isn't having anything else being done to it before the 1 minus happens, make u 1 minus ln x. It'll be easier. So this actually shows why I did one in the other and not why I include that number in one and not the other. So I think these are two good side-by-side examples. The reason I'm bringing the 1 minus along with it is because that ln x has nothing else being done to it before it has the 1 minus being done to it. Here, you've got a cube cosine before you do the 1 minus. That's why I don't bring the 1 minus into the u. Here, it's just ln x, and you're going to do 1 minus it, bring it along for the ride. So there are your two u's. Find your du's. They're both really simple. Fix your coefficient problem, which I think is going to be the same fix in both cases. Rewrite. Be a master of u substitution. And of course, Jack's whistling while he works.